Welcome to lecture 5.5 over trigonometric equations. This particular chapter is kind of the denouement of the chapter. It's putting everything that we've picked up throughout chapter 5 on analytic trigonometry, all of the identities and the formulas and stuff, and saying, okay, now use these to help solve trigonometric equations. So we'll start this section, of course, with looking at the objectives, and then we'll move into, okay, well, what is a trigonometric equation? So let's move forward. Okay, so you can see here that we are going to basically just be solving equations the whole time. So this is pretty much all just example equations, this entire section. So we're going to learn to find all solutions of a trigonometric equation, solve equations with multiple angles, solve trigonometric equations in quadratic form, so factoring comes in a little. So using factoring to separate different functions in trigonometric equations, and using identities, and then using our calculator. Okay, so just a definition here, a trigonometric equation is an equation that contains a trigonometric expression with a variable within it, such as the sine of x. The values that satisfy such an equation are its solutions. So just to point out, if I have the sine of x equaling some value, I'm trying to figure out what angle can I take the sine of and get that value. There are trigonometric equations that have no solutions. When an equation includes multiple angles, the period of the function plays an important role in ensuring that we don't leave out any solutions. So I'll be reminding you of all that stuff on the first, let's see, 1, 2, 3, 4, 5 equations that we're going to work, and we're going to work 7 total. On the first 5, I have also put the unit circle there. So I'll point out on the unit circle what we're doing algebraically. Okay, so the first thing that we want to do is find all solutions of a trigonometric equation. And the trigonometric equation that we're going to look at first is 5 times the sine of x equals 3 sine of x plus the square root of 3. Our first step, and these steps are on your note sheets, I forgot to put them on the PowerPoint here, but the first step is to isolate the function on one side of the equation. The second step is to solve for the variable. So the first thing I want to do is isolate my trig function. So I need to get the sine, or 3 times the sine of x, over with that other sine of x so I can put them together. So I'm going to subtract 3 sine of x from both sides. There's a 0 pair, so I'm left with 0 plus the square root of 3 on the right-hand side. And if I have 5 of these things called sine of x, and I take away 3 of these things called sine of x, I'm left with 2 sine of x, equaling the square root of 3. Okay, so I still need to divide by 2 to isolate the function. And that leaves me with the sine of x equaling the square root of 3 over 2. Okay, so this is where the unit circle comes in. We want to find all of the solutions possible, but we'll start with the ones that are visible on the unit circle. And then we'll just expand from that by rotating it through the circle infinitely. So let me point out, by the way, we get our sine value from the y-coordinate. So the y-coordinate is square root 3 over 2 when x is pi over 3. And when x is 2 pi over 3, we also have square root 3 over 2 as our sine of x. So here's where we are so far. The solutions for just, one revolution through the unit circle, so that's 0 to 2 pi, are pi over 3 and 2 pi over 3. But we want to find all possible solutions. So we just want to state both of these solutions as they occur according to how many times you're rotating through the plane. So all solutions we have pi over 3, and as long as I'm making some amount of full rotations through the plane, so the 2 pi makes one full rotation through the circle there. The n says I can do that as many times as I want to. So some multiplying by some integer n. So let's just pretend, for the sake of example, let's say we start at pi over 3 and I make a loop through. That's pi over 3 plus 2 pi. So n would be 1 in that case. And look, I landed at the same spot I stopped at. So I make another rotation through. That's pi over 3 plus 4 pi over, 4 pi over 3 plus 4 pi, because 2 pi is one rotation through, so 4 pi would be 2. N would be 2 in that case, so 2 times 2. If n is 3, that's 6 pi, so I've made another revolution through. So hopefully that helps you understand how I have that particular solution written. And it's the same thing for 2 pi over 3. So if we start at 2 pi over 3, as long as we're making full rotations through the plane, we're still going to land at 2 pi over 3. So all solutions for that equation is given by pi over 3 plus 2n pi and 2 pi over 3 plus 2n pi. Okay, so with this one's a little more involved than that first one was, but it's not too bad. We'll take a look. So we're given that the tangent of 2 x is equal to the square root of 3. Well, if you take a look, by the way, the tangent is equal to y over x. And I'll show you how you find this in just a minute. We end up seeing that the tangent of pi over 3 is equal to the square root of 3. Here's how we figured that out. The tangent is y over x. So if you look at pi over 3, if I divide y by x, I have the square root of 3 over 2 divided by 1 over 2, which is the square root of 3 over 2 times the reciprocal 2 over 1. My 2's divide out, and I'm just left with the square root of 3. So that's how we figured out that the tangent of pi over 3 is the square root of 3. So since I have this relationship set up right here that tangent of 2x is the square root of 3, and I also know that the tangent of pi over 3 is the square root of 3, then that means, let me get a different color here because this is important, that means that 2x has to equal pi over 3. So that's what I'm going to set up. 2x equals pi over 3. Multiply both sides by 1/2 to isolate the variable. These 2's cancel out. And I get x is pi over 6. So the deal, though, is that that's just for that first quadrant, and I want to know, well, what about moving through the entire circle? And we know from previous lessons that the period of the tangent function is pi. So if I want to talk about all solutions, oh, I should have put it on before I did the math here. Let me erase this and go back. It's not too different. I just forgot to put all revolutions on there before I worked the equation, even though it's sitting right here on my paper. And in the last lesson, I told you I was going to come with my brain for this one. Apparently, I've come with more of it than I did for the last lesson, 5.3, but not the total thing. So we have 2x equals pi over 3, and then because the period of tangent is pi, I can say, well, that's going to be the same thing for any integer multiplied by pi. So any period of pi there. So now let's multiply both sides by 1/2. So I'll multiply by 1/2 here and here. All right, so that still leaves us with x, and then I still have pi over 6 here. But now I can add on some integer times pi over 2 for the rest of the solutions. So we want to know, well, what are the possible solutions between 0 and 2 pi? And the integers that fall between these numbers, we have 0, 1, 2, and 3. Because once we get to pi, that's 3.14. So let's go ahead and do this figuring for 0, 1, 2, and 3. So I have x equals pi over 6 plus 0 times pi over 2, and that just leaves me with pi over 6, because that's pi over 6 plus 0. I have an n of 1, that's pi over 6 plus 1 times pi over 2. I'm going to need to get a common denominator there, so I'm going to go ahead and multiply this by 3 over 3 to get 6 in the denominator. So that's pi over 6 plus 3 pi over 6, which is 4 pi over 6. And actually, I think I must have had a typo in here. I believe that they're asking us to do this between an interval of 0 to pi, and I think I just put 2 pi as a habit because the solutions only took us 0 through 3, and if we were trying to go to 2 pi, we would need to go all the way up to 6, so I must have mistyped that. So please make that correction on your notes. And 4 pi over 6 simplifies to 2 pi over 3. All right, when n is 2, I have x equals pi over 6 plus 2 times pi over 2. Those 2's divide out. I do need to go ahead and get a common denominator though, so I'm going to multiply by 6 over 6. And that gives me pi over 6 plus 6 pi over 6, which is 7 pi over 6. All right, and finally, an n of 3, we have x equals pi over 6 plus 3 pi over 2. I'm going to go ahead and get a common denominator. I need to multiply by 3 over 3. So that is pi over 6 plus 9 pi over 6, which is 10 pi over 6. So let me just highlight all of our solutions to the equation here. We have pi over 6, 2 pi over 3, 7 pi over 6. Oops, that reduces. 10 pi over 6 is the same thing as 5 pi over 3. So there's our last solution for the interval 0 to pi. All right, we'll move forward. Okay, so solving a quadratic equation in quadratic form. So we start out, and this one really is from 0 to 2 pi because the period for cosine is 2 pi. So let me get my black pen. 4 cosine squared of x minus 3 equals 0. So I'm going to start isolating my function. First thing I'm going to do is add 3 to both sides. So 4 times the cosine squared of x is 3. Divide both sides by 4. So cosine squared of x is 3/4. Now I need to take the square root of both sides. And I get the cosine of x is positive negative square root of 3/4, which is the same thing as positive negative square root 3 over square root 4, which is the same thing as positive negative square root 3 over 2. So now I need to go identify, okay, well, when is my cosine, or my x value, when is my cosine either positive or negative square root 3 over 2? And that occurs, I'll point it out on the unit circle, it occurs at pi over 6, also happens at 5 pi over 6, and 7 pi over 6, and finally 11 pi over 6. So my solutions are pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. All right, so this time we're going to use factoring to separate different functions from each other. So here we go. And then once we factor, since we'll get this thing set equal to 0, we'll factor and use the zero product property. So let me get my black pen. We start out with the sine of x times the tangent of x equals the sine of x. I've got to get this thing equal to 0 so that I can use the zero product property. So I'm going to subtract the sine of x from both sides, and that leaves me with sine of x tangent x minus sine x equals 0. And here's where I have to use my factoring skills. Both of my terms have a factor of sine of x. And when I divide that out, I'm left over with tangent x minus 1. And that's equaling 0. So now I have my equation looking like some product equaling 0. So since I'm multiplying things together to equal 0, I could assume, I could assume that I'm multiplying with 0 because that's the only way to multiply and make 0. So that's what I do is I said, well, how can either of these be 0? So the sine of x equals 0. That occurs when x is 0 or x is pi, and I'll show you where that lives. When x is 0, the sine of x is 0, and when x is pi, the sine of x is pi. Okay, I'll do the tangent in a different color. I'll do it in blue here. So the tangent of x minus 1 equals 0. Add 1 to both sides. And so now I'm trying to figure out, well, when is the tangent of x going to equal 1? Well, the only time that the tangent is going to equal 1 is when I'm dividing something by itself. So when I'm dividing the y value by the x value, and those two values are the same. And that occurs at pi over 4. See, I've got square root 2 over 2 and square root 2 over 2. And it also occurs at 5 pi over 4. I've got negative square root 2 over 2, negative square root 2 over 2. So the tangent of x is 1 when x is equal to pi over 4 or 5 pi over 4. So I'm just going to box in our solutions. So we have the solution 0, pi, pi over 4, 5 pi over 4. Okay, here we're going to use an identity to solve. So, you know, with these equations, you kind of have to be clever, because sometimes it can be difficult to, oh yeah, that's what I could have rewritten that as. So I'll just point out here with this particular equation, I've got cosine of 2x being added to the sine of x equaling 0. So I've got two different functions happening here equaling 0. So if there's some way that I could rewrite one of them in terms of the other, then that would at least get me moving towards some solutions. So I'm recognizing right now the cosine of 2x. In our last lesson, 5.3, we learned the identity that the cosine of 2x is the same exact thing as 1 minus 2 sine squared x. And I'm adding that to sine of x, and that's equaling 0. Now, here's another thing you have to be clever about and recognize. I've got a sine squared term, a sine term, and a constant term. So that fits the mold of being a quadratic. So I can rearrange this as 2 sine squared x plus sine of x minus 1 equaling 0. All right, so I'm going to, off to the side, do some factoring for you. So this would be like having 2x squared plus x minus 1. So 2x squared plus x minus 1. If I multiply 2 and negative 1, I get negative 2. And the factors that multiply to make negative 2 but add to make positive 1 are 2 and negative 1. And so I rewrite 2x squared plus 2x minus x minus 1. So GCF of 2x here, so I have x plus 1. GCF of negative 1, so x plus 1. So this factors as 2x minus 1 times x plus 1. All right, so I can rewrite, I can input the sign of x in there, and oh my goodness, I've made another mistake. I flip-flopped my signs. 2x. Okay. So notice this is the negative 2 sine squared of x, so this should be negative, and this should be positive. The only thing that this does in our factoring over here is it changes the signs on the inside. So I have 2x plus 1 and x minus 1. Sorry about that. So I'm going to come back over here and rewrite this in its factored form and plug back in my sign of x's where I was just using x's over here when I was factoring. So I have 2 sine x plus 1 times sine x minus 1. So all I did was wherever I saw x in my factored form over here, I just plugged in sine of x because that's where it came from. And that's equaling 0. So now, once again, I have a product equaling 0. I can use my zero product property to solve. So 2 sine of x plus 1 equals 0. And sine of x minus 1 equals 0. So I'm going to subtract 1 from both sides. So 2 sine of x is negative 1. Divide both sides by 2. So the sine of x is equal to negative 1/2. And the sine of x is equal to negative 1/2. So I'm looking for a y value of negative 1/2. That happens at 7 pi over 6, and it also happens at 11 pi over 6. So in this first case, x is equal to 7 pi over 6, or 11. Oops, I wrote pi instead of 11. It's a habit. There we go, easily fixed. 11 pi over 6. And now let's look at the sine of x minus 1 equals 0. Add 1 to both sides. So I have sine of x equaling 1. So I'm looking on my unit circle where my y value is equal to 1. And that happens at pi over 2. So x is equal to pi over 2. So this time I have 3 solutions. I have the solution 7 pi over 6, 11 pi over 6, and pi over 2. Okay, so for these last two, we're actually using our calculator. So I would encourage you to double check your calculator and make sure that it is in radians right now because we are working in radians. You do that by just clicking the mode key. That is second from the left at the top. And look down and you'll have the ability to toggle between degrees and radians, and you want to make sure your calculator is set to radians. Let's go ahead and work this equation, solve this equation. So we have the equation, the tangent of x equals 3.1044. Well, notice I'm trying to figure out, okay, what angle can I take the tangent of and get that value? So I can know that value by taking the inverse tangent of what was formerly what I was equaling. Oops, let me get my, there we go. And get my pen back. Here we go. 3.1044. So I go to my calculator and I do inverse tangent of 3.1044, and I get that x is approximately 1.2592. Now, we know that the tangent is positive, so we're trying to find the tangent of x for positive 3.1044. We know that the tangent is positive in quadrants 1 and 3. So tangent is positive in quadrant 1 and quadrant 3. So in quadrant 1, I have that x is equal to, or I'm sorry, is approximately 1.2592. To go from quadrant 1 to quadrant 3, so say I have a point here and I want to go over to there, I have to add pi, which is half the rotation through the circle. So my solution in quadrant 3 is x is approximately pi plus 1.2592. And when you do that in your calculator, you get that x is approximately 4.4008. So I have two solutions to this equation, approximately 1.2592 and approximately 4.4008. And notice they ask us to take that out to 4 decimal places. All right, last one. Okay, so we have the equation sine of x is equal to negative 0.2315, and I'll go ahead and point out that the sine of x is negative in quadrants 3 and 4. Okay, so we'll go ahead and use our inverse sine function to rewrite this. So x is equal to the inverse sine of negative 0.2315. And when I put that into my calculator, I get that x is approximately 0.2336. Okay, so that 0.2336 is the value in quadrant 1. But we need to know for quadrant 3 and for quadrant 4. So for quadrant 3, once again, I just want to go straight across 180 degrees, so I just need to add pi to that value. But for quadrant 4, that's a little trickier to think about. So I'll think about something here. If I go all the way around, that's 2 pi. So from here to here is 2 pi. So what I do to figure out that angle is I subtract the 0.236 from 2 pi. So I'll show you what that looks like algebraically. So for quadrant 3, I have that x is approximately pi plus 0.2336. And when I put that into my calculator, I get that x is approximately 3.3752. And for quadrant 4, x is approximately 2 pi minus 0.2336. And when I put that into my calculator, I get that x is approximately 6.0496. So I've got two solutions here. I have x is approximately 3.3752 and x is approximately 6.0496. And that's all I have for you. The next lecture I'll be doing will be a test review. So this test coming up will cover 5.1, 5.2, 5.3, and 5.5. Happy homework and happy studying.